Hello everyone, this is Mr. Deaver again with our lesson for this week. Now, last week we talked about polar and nonpolar bonds. So this week we're going to talk about the next step, polar and nonpolar molecules. Let's review some key ideas from last week first. Last week we learned about electronegativity. Now, electronegativity is how much an atom attracts electrons. Last week we used this table of electronegativities. So we know that some atoms, like fluorine here, has a very high electronegativity, and some atoms have a lower electronegativity. Now, atoms with a high electronegativity have a strong attraction for electrons. They exert a force and pull electrons towards them, like this atom is pulling electrons towards it. It has a high electronegativity. Electronegativity is the reason why we have polar and nonpolar bonds. If you look at Cl2, both Cl atoms have the same electronegativity. They both have a value of 3.0. That means that these two Cl atoms share electrons equally, and the electrons do not get pulled to either side. We do not draw an arrow because there's no force pulling on the electrons. Both sides are the same, so this is a nonpolar bond. If we look at HCl, though, the atoms have a different electronegativity. Cl is 3.0 and H is 2.1. So Cl, chlorine, has a higher electronegativity. Since it's more electronegative than hydrogen, it pulls electrons towards it. So we draw an arrow to show the force pulling the electrons to this side. Well, Cl gets more electrons, so the atoms share electrons unequally. The two sides are not the same, they're different sides because there's more electrons on this side. Since electrons have a negative charge, this side is partially negative. This symbol here means partially. So this side is partially negative since there are more electrons over here, and this side is partially positive because there's fewer electrons over there. Well, since there's two different sides of partially positive and partially negative, this bond is polar. The two sides are different, like the North Pole and the South Pole of Earth. Now, before we look at polar and nonpolar bonds, polar and nonpolar molecules, let's look at a short experiment here. The person is rubbing this balloon, and whoa, look at that. We see the water bending towards the balloon. Why is water bending towards the balloon? Well, to explain this, we have to learn about polar and nonpolar molecules. Now, we're going to practice together to determine if molecules are polar or nonpolar. Well, in the past, we have drawn Lewis structures, and when we've used the Lewis structures to determine the molecular geometry, like whether something is linear, trigonal planar, bent, tetrahedral, trigonal pyramidal. Lucky for you, you don't have to do this. Okay, every time we're going to give you the molecular geometry and show you the three-dimensional shape. So you don't have to figure this out. However, it may be helpful to review this document, and this document is posted on my MCPS classroom, because to figure out polar and nonpolar molecules, you have to think sometimes in 3 dimensions. Okay, here are the steps to determine if a molecule is polar or nonpolar. First, for each bond, if the bond is polar, we draw an arrow towards the more electronegative atom. Okay, well, in this molecule there are 2 bonds. Here's one bond between this O and C, and here's a second bond. So we have to draw arrows, if necessary, for the bonds. Well, let's see. Let's look at C, carbon, and O. Yep, oxygen is more electronegative than carbon. So which way do we draw the arrows? We draw an arrow towards the more electronegative atom. So we're going to draw arrows from the C to the O in these 2 bonds. Okay, so now that we drew our arrows, let's see if the molecule is polar. Well, if the arrows all point in the same direction, the molecule is polar. That's because a polar molecule has a positive side and a negative side. If the arrows all point in the same direction, then the electrons are all getting pulled to the same side. However, is that true here? Do the arrows point in the same direction? Nope, they don't. These 2 arrows point in opposite directions. So, step 3 says, if there are no arrows, or if the arrows cancel out and point in opposite directions, then the molecule is nonpolar. So is that true here? Do the arrows point in opposite directions and cancel out? Yes. Okay, so this molecule is nonpolar. Now, this is maybe a strange idea, but let's think about an example, an analogy. Think about this game, tug of war, where you have different people pulling on different sides of a rope. Well, if the 2 people are equally strong, if they pull in opposite directions, then the forces cancel out. If the forces pull in equal and opposite directions, then they cancel out. And is the rope going to move? No, the rope is not going to move. It's going to stay still. Well, same thing here. There's forces pulling the electrons in opposite directions, but they're equal and opposite. So do the electrons move? No. All right. So they don't get pulled to this side or that side. Both sides, all sides of the molecule are the same. So CO2 is nonpolar. Okay, let's look at another example, PCl3. And again, we've shown you the molecular shape of PCl3. All right, well, for each bond, let's draw the arrows. So let's look. Here's P, that's 2.1. Chlorine is 3.0. So we need to draw our arrow towards this atom, the chlorine. All right, so that's the chlorine. So we'll draw an arrow there. That's our chlorine. We draw the arrow there. And here's our chlorine, so we draw the arrow there. So there's our phosphorus. There's our 3 chlorines. We have our 3 arrows. These arrows represent forces pulling the electrons. Well, if the arrows all point in the same direction, then the molecule is polar. Now, this is a tricky case. Do the arrows all point in approximately the same direction? The answer is yes. They all point generally down. Not totally, but generally down. So that means that this side of the molecule, is it going to have more electrons or fewer electrons? This side is going to have more electrons. So is this side going to be partially positive or partially negative? Okay, this side is going to be partially negative. So I'm going to draw my partially negative symbol here and my partially positive symbol here. Right? It's hard to draw these symbols on the mouse on my computer, but remember this is what the symbols actually look like. Okay, they're partially positive and partially negative. So yes, these arrows are generally pointing down in this direction. Not exactly all pointing completely down, but this side down here is going to have more electrons, and this part up here is going to have fewer electrons. All right, so we have a positive side and a negative side. Guess what? This molecule is polar. All right, let's look at another example here, CF4. Okay, well, we need to look at our bonds. For each bond, we need to draw an arrow towards the more electronegative atom. Carbon is 2.5, fluorine is 4.0. So do we need to draw arrows? Yes. Which direction do we draw the arrows? Towards the C or towards the F? Towards the F's. So we're going to draw 4 arrows towards the F's. Now, remember, this is a 3-dimensional molecule. We don't really see the 3 dimensions here, but this molecule is going, this atom is coming out at us, and this one's going back. So this is a tetrahedral 3-dimensional. Well, what do you think? Are these arrows all pointing in the same direction, or are the arrows pointing in opposite directions and canceling out? Well, they are pointing in opposite and different directions. Okay, it's kind of like in this picture here. Now we have 4 different things pulling, right? Well, if all these 4 forces are pulling in equal and opposite directions, they cancel out. So imagine that these 4 people are all equally strong and pulling equally in these directions. Will this center part move? No, it will not move. And same thing here. These electrons do not get pulled to any side because the forces cancel out. So is this molecule polar or nonpolar? It is nonpolar. Okay, let's look at another example. We have 2 more examples to look at. This is CH3Cl. And again, we've shown you the shape. Now, we've shown it a little bit differently. We've shown it with these different symbols, but really, these symbols mean the same thing as this. It's showing a tetrahedral shape. So this H is coming out in space, and this H is going backwards. All right, so first we need to, for each bond, if the bond is polar, draw an arrow towards the more electronegative atom. So we have CH bonds and a Cl bond. Now the CH bond should be easy. Is that bond polar or nonpolar? That bond is nonpolar. CH bonds are always nonpolar. We learned that last week. Always, always, always nonpolar. So do we draw arrows for CH bonds? No, we do not draw arrows for CH bonds. Nonpolar bonds, we do not draw arrows. What about C and Cl? Okay, here's carbon 2.5, Cl 3.0. This bond is polar. They have a difference. So where do we draw our arrow? Towards the C or towards the Cl? Towards the Cl, the more electronegative atom. So this arrow is showing a force pulling the electrons up in this direction. Now, step 2 says if the arrows all point in the same direction, the molecule is polar. If there are no arrows, or if the arrows cancel out, the molecule is nonpolar. Well, what do you think? Are the arrows pointing in the same direction or opposite directions? Well, there's only one arrow. So yes, all the arrows are pointing in this direction. Even though there's only one, it's pointing in this direction. So the electrons are getting pulled up here. So this side of the molecule is going to be what? Partially negative or partially positive? Partially negative. There's more electrons on this side. This side down here with the H's is going to be partially positive because there's fewer electrons. So this molecule has a positive side and a negative side. Is the molecule polar or nonpolar? It is polar. The electrons are getting pulled to this side, so this is our negative side. There's two different sides, just like the North Pole and South Pole of the Earth. This molecule is polar. Okay, one more example. Let's look at H2O. Okay, we have an H and O bond here. O is a value of 3.5, H 2.1. So we're going to draw our arrows towards the O here because that's the more electronegative atom. And what do you think? Are the arrows pointing in about the same direction or are they pointing in opposite directions? They are pointing in about the same directions. Both the arrows are kind of pointing up here. So this side is going to be what? Partially negative or partially positive? Partially negative. This side down here, partially positive. The electrons get pulled to this side, so that makes this side of the molecule a little bit more negative. So, is the molecule polar or nonpolar? It is polar, right? Remember, these arrows aren't pointing in exactly the same direction, but they're both pointing approximately up. So the arrows don't have to be pointing in exactly the same direction, just approximately. Similarly, remember PCl3, these three arrows were not pointing in exactly the same direction, but they all were pointing approximately down this way. So we know that water, H2O, is a polar molecule. Well, remember that the balloon made the water bend. Why is that? Well, remember, the person rubbed this cloth on the balloon. When the person rubbed the cloth on that balloon, that made static electricity. It made the balloon negative. That means that the water all oriented itself, it positioned itself so that the positive sides were all over here and the negative sides were all over here because we know that positives and negatives are attracted. So the water spun around and oriented itself, positioned itself so that it's like this. And then this positive side here of the water was attracted to this negative side of the balloon. And that's why the water bent. Okay, now you have some practice on my MCBS classroom. Now, you don't have this on paper. However, I recommend that you try to draw these molecules on paper and practice these steps. Practice drawing the arrows and using the steps to determine if the molecules are polar and nonpolar. Okay, good luck.